Welcome everyone to the AISD Forum. This is session number 6 of our Arctic Security Series. So we are very pleased to have Dr. Madeline Lee from the Norwegian Applied Research Foundation, SINTEF, with us today. Dr. Lee has a Master of Science and a PhD from McMaster University, all in geophysics. Prior to SINTEF, Dr. Lee was a staff research officer at the National Research Council of Canada. Dr. Lee has applied robotics and geophysics, various sensing methodologies to diverse application settings such as environmental protection, resource exploration, and anti-submarine warfare. Today, thanks to Dr. Lee, we get to look at a more foundational aspects of AI and machine learning, that is the data acquisition and conditioning part of the pipeline. So the Arctic is an environment that really highlights the complexity of acquiring data from the analog world. Right? So it remains one of the most challenging environment, also from the perspective of domain and situational awareness. So with this just a brief setting of context, I will pass on the floor to Dr. Lee.
All right. Can you hear me all right?
Yes.
Okay, perfect. Excellent. Well, good morning and good afternoon to those that are online. I really appreciate the opportunity to be here to speak today a little bit more on the physical sciences side. And as mentioned, I am a researcher with SINTEF. And so I'll be presenting Unlocking the Arctic, Geophysics and Security, Geopolitics, and Resource Exploration. So I'm with SINTEF Industry, which is a component of SINTEF, and I'm in an applied geosciences group, specifically geophysics. And as we've been talking about over the past weeks, there's a lot of focus on the Arctic for several reasons. There's a lot of sustainability development in the side of green energy, such as wind energy, natural hydrogen, and offshore resources. There's been a lot more emphasis on deep sea minerals as well. And sorry, just one second. Yeah, a lot more emphasis on deep sea mineral mining, which Norway just recently opened a portion of the margin to be able to explore for deep sea minerals. There's looking at animal enumeration, as well as the impact of climate and industrial development in the Arctic on permafrost and peat. And because of this, there's been a lot more emphasis in terms of grant proposal calls and how the funding is being achieved. For example, Nordforsk within Scandinavia had a call earlier this year, which was on sustainable development of the Arctic. And I think it quite nicely emphasizes what the seminar series has been for AI for SD over the last few weeks. We're looking at security, natural resources, and societal changes. These 3 components really have to work together in order to be effective. And more specifically, I think it very well lays out the idea of that we need to be interdisciplinary. There needs to be a sustainable development. There needs to be a benefit to the Arctic. And we always need to make sure that we have indigenous perspectives to be able to have direct engagement and data dissemination with the remote communities and First Nations. So brief overview on what I'll be talking about today. So I'm a physical scientist. I am not an AI or machine learning practitioner, nor am I a security and defense expert. However, as a physical scientist, I feel that we have skill sets as well as development. We can provide development on a number of different of these areas that are highlighted here. So I'll start with a bit of a background as to why I'm here today, looking at dual use, specific use cases, and some of the challenges of doing these operations in the Arctic. So throughout my career as a geophysicist, I've always kind of had one foot on either side of this civilian defense market. I first got into geophysics working at the Geomagnetic Laboratory of Natural Resources Canada. And as a scientist, my role was looking at the geomagnetic monitoring service, which was key for space weather, which I'll talk a bit more about in a little bit, and supporting calibration of professional and military grade magnetic compasses. This is incredibly important for navigation. Then moving on to Flight Research Laboratory at the National Research Council of Canada. So as mentioned, I was a research officer. And this has been a large component of my professional career, looking at payload and sensor integration on a number of specialized and customizable rotary and fixed wing aircraft, and both crewed and uncrewed. Now, the reality is that here we have the Flight Research Lab in Ottawa, and you can see a slew of the different fleet that we have from, for example, the Convair 580. We have a Falcon, we have a Twin Otter, we have a T-33, and each aircraft has a specific set of skills. It can fly at specific heights, and it can carry different sensor payload capacities. And so being able to offer all of these opportunities to different clients, collaborators, government, and industry really allow us the opportunity to finesse our scientific method. And here I always like to highlight the Uplands campus where the Flight Research Laboratory was. And so here there are two wind tunnels that you can see. So here's a 9-meter wind tunnel, and it's quite large and would actually do operations for looking at aerodynamics of trucks. And over here you have a trisonic wind tunnel that actually goes up to Mach 4.25. An example here of the Convair 580. And what's fantastic about the Convair 580 is that it is a real workhorse for a number of different sensors. So you can see a number of sensors on the wingtips here. And we have the ability to put them in the nose, upward and downward. So we have upward and downward looking LiDAR. And so this particular aircraft does operations everything from atmospheric physics to magnetic anomaly detection for the application to anti-submarine warfare. And it is completely demagnetized, or I shouldn't say demagnetized, but magnetically characterized. Here we have operations of doing search and rescue for downed aircraft as an analog, integration of sensors onto a uncrewed aircraft. This is the Brycan TD-100 Sub Hunter. And then working actually on the aircraft itself, this particular scenario here was working with Canadian Forestry Services to look at forest fires, wildland fires in real time and with broadband infrared. So moving on to uncrewed aircraft. So near the end of my time at NRC, I had the opportunity to gain more experience in uncrewed aircraft. And again, this is kind of straddling between the civilian and the defense market. And so collecting magnetic data throughout Norway, you can see a magnetic sensor here on a custom rotary drone from the Helmholtz Institute in Germany. But more recently, and what I'll talk about in more detail today as well, is my time with SINTEF industry and the implications within Arctic research. And so again, this is principally uncrewed aerial vehicles, looking at different techniques and developing new processing methodologies for geohazards, green energy transition, and archaeology. So for geophysics, it's the study of the physics of the Earth and its environment in space. One emphasis is the exploration of Earth's subsurface using physical properties measured at or above Earth's surface. So anywhere from space to airborne to surface to even subsurface in the context of a borehole. And using that together with mathematical models, we're able to predict those properties that allow us to determine different targets. Now, there's many different applications from the natural resources sector, geohazards, infrastructure, environmental, defense, and planetary. And so basically, there's a number of different areas that we can utilize the geophysical method, variety of geophysical methods. It all depends on what the physical property is that we're interested in finding. And so this is just an example of the different types of geophysics we can deploy. The most well-established and probably the most classical method being potential fields, such as magnetics and gravity. A lot maybe quite well known with electromagnetics, your electrical methods, acoustic or seismic, and then we have radiometrics looking at levels of percentage of uranium, equivalent thorium and potassium, and then even spectral imagery. So for example, acoustic methodology would be used highly within oil and gas sector versus something like spectral imagery, hyperspectral, multispectral may be implemented more often from a satellite mission. So in terms of this property, we need to think about what it is that is our target. And our target is our signal. And everything else is noise. But at the end of the day, one person's signal could be another person's noise. And this is where we're starting to get into that dual use. And so we think about the proverbial needle in the haystack. And so in some cases, we're looking for the needle, but there are those that actually are looking at the haystack. So this is where we can actually see some of the original origins of geophysics. And what we have here is one really big needle. So in order to find our target, in this case, a submarine, we need to be able to remove the haystack. That geological context, the impact of the water column, all of these other environmental sources of noise. Now, in terms of this particular configuration, we have magnetics, active acoustics, passive acoustics, and radar. But for today, I'll focus mainly on magnetics with a little bit in terms of radar, more specifically ground penetrating radar. So just to really have a brief overview of how the magnetic survey works, just as we move on. So basically we have some sort of subsurface target. So for example, here, this could be an unexploded ordnance, a UXO, that's below the surface of the Earth. Now, Earth has a magnetic field, and so this ambient magnetic field induces a field within this magnetic material. And if we come along with our magnetic sensor at the surface, whether it be walking on foot or from an aircraft, we can actually start to measure the intensity of this magnetic field. And it will result in a profile that we see here. And basically the flux gives us a representation of an intensity. Now, the thing is, this is nice and simple, but it's never just as simple as that. Whenever we conduct a survey, whether it be from ground or airborne, there's going to be a lot of this noise that I've mentioned. And so that could be from the sensor, the magnetic sensor itself. It could be from a car nearby, somebody happens to drive by. It could be from an aircraft itself where we have induced eddy currents along the fuselage. We need to start understanding what are all of the individual components that are being measured by the magnetic sensor. And if we take all of these profiles and we put them together, we're able to get a snapshot of the subsurface. And this is where geophysics really stands apart, where not only can we get information at the surface, we can get subsurface information. And again, with respect to subsurface information, talking about ground penetrating radar. And in terms of this, we actually have, we have once again, our geophysical operator at the surface here. And we have a transmitter and receiver of radio waves or a radar pulse. And so we're actually able to look at the transmitted signal to the reflected signal in terms of its time and actually start to get an idea of intermittent layers. So we're actually getting an interface or a boundary. And so going through the general processing of a number of different corrections, filtering, even to topographic corrections, we end up getting our processed GPR data that you can see here. So for example, this would be rock. This is the interface between ice and snow. So looking a bit at dual use, I believe it was Abby a couple of weeks ago or last month who talked about there's always a sense of dual use, and we need to acknowledge it. It's really hard to separate the two. So for magnetics, it definitely has an origin within the defense market. And so the original magnetic sensor or magnetometer was designed and implemented during World War II, for example. So you can see the sensor here, and it was principally used for submarine detection. But it was acknowledged after the fact, after World War II, that it could actually be used in mineral exploration, and it was implemented for iron ore detection. Because again, we have similar properties between submarine and this iron ore target that we're trying to find. Further on, we have, these additional airborne magnetometers that were developed. For example, phase one, which was quite heavy at 86 kilograms, so certainly can only go on an aircraft. But then, courtesy of the space age in the 50s, there was a lot of technological development, and the sensor was actually able to be decreased in size from 86 to 34 kilograms, but still keeping us restricted to an aircraft. If we fast forward over the decades, the sensors have decreased in size, weight, power, and cost. And I think this is true for most technology that we could think about. It's becoming much lighter, smaller, and we're able to use a lot less power. So moving from a traditional crewed aircraft, we can actually start to put these sensors, for example, the Geometrics G24 or MADXR from CAE, onto a uncrewed aircraft. So you can see the dual wingtip pods on this particular TD100 right here. Now, these are a couple kilograms, but the development again of the technology allows us to go even smaller. And so we have a number of atomic sensors here, atomic magnetometers, that, as you can see, the penny for reference, we're talking 300 grams. And so this gives us the ability to not only just put one sensor on board or two, we could actually put several sensors on board and in synchronization. And with the development of quantum technology, there's been a lot of these more in terms of from the laboratory on the optical bench developments. So we're seeing magnetometers that actually utilize the idea of nitrogen vacancy diamond technology. And so what's fantastic about this is that a limitation of the equipment that we use, with magnetic sensors, this is offering a solution where we actually don't have a dead zone. We're limiting the amount of data loss is what the proposition is. And as these sensors get better in terms of size, weight, and power, their sensitivity is also getting better. We're getting into very high resolution data sampling. We can get very high frequency samples. And because we can have a higher frequency sampling rate, we can collect more information about very complex targets. Now, dual use again can overlap if the target has a similar frequency range. So I've shown here brain images of brain scans because there's a very strong, or there is an overlap between the sensors and the sensing technology used by brain science as those within defense science. And so you're starting to see actually these collaborative webinars and seminars between physical scientists, biologists, and non-traditional defense scientists so that there can be this data exchange. And an example here is within digital signal processing. So on the left here is drone-borne magnetic data. And as you can see on the top panel, it's extremely noisy. We can't really see too much, but by doing our digital signal processing, we can start to see some geological content. And the same is implemented within brain science as well. We have a raw EEG, and by breaking it down into its frequency components, we can start to see different targets that we're interested in. And with this increase in resolution, sampling rate, and quality of the instruments, it's giving us, when I say us, the geophysicists, an opportunity to expand our applications. So in 2024, the Society of Exploration Geophysicists had their first online forum on detection of explosive remnants of war. And This was a recognition that the geophysics community was developing technology that had a direct overlap with the defense market, and recognizing that there should be an exchange of knowledge and discussion. I highlight here, for example, from the University of Maryland, uh, Daniel Lathrop, Ved Lichik, and Heidi Myers, who actually created a very innovative system with a drone that had multiple sensors on it, from a broadband infrared system, sensor, magnetometer, and partnering that with artificial intelligence made a very effective system to be able to detect buried landmines. As well as we have these UMEG solutions, this UMEG solutions sensor platform, drone platform with an innovative design when it comes to the magnetometer system. And because of this configuration, we're able to pick out a UXO more readily because we're able to capture a very specific frequency range. Another important aspect that I've come across a lot is GPS denied navigation. And so typically what's been applied is something called SLAM or VSLAM. And so this is using LiDAR, which is light detection and ranging, but to do simultaneous location and mapping. So it's the idea of creating a point cloud around the system, the moving system, whether it be a vehicle, aircraft, or a submarine or subsea vessel, to create its own environmental map. And this is great. However, we're starting to also look at the benefit of using magnetics. So we can look at the crustal magnetic anomaly map that you see here. Data has been collected for decades. It's very well mapped. And in essence, what could happen is that you have a subsurface vessel, submarine, for example. It does not have access to GPS, but it is well understood in terms of where specific magnetic anomalies may exist and can orient itself that way. So I want to talk a bit about a couple specific use cases. So I mentioned earlier space weather, and we're on the topic of magnetics. So I wanted to bring up the idea of that um, geophysics is really important for understanding the like when we get that transition from the sun, how it interacts with the magnetic field of the earth and how it impacts the technology at the surface. So at the sun, we have our coronal mass ejection or a solar flare, which actually emits this electromagnetic energy, and it hurtles towards the Earth, and it can intercept with our satellite systems, creating degradation, radiation damage. And then we actually have these disturbances and enhanced currents along the ionosphere, the magnetic field, and what this actually does is that it can impact our navigation system. And so this impacts our aircrafts. And so we also have a lot of induced currents within our electrical grid on the ground. So we can have an induced current in a power system, creating saturation within the transformers. And we can have an induced geoelectric field within a pipeline in the subsurface. So it's going to cause increased corrosion within the pipeline and more quickly. So we need to think about protection, corrosion protection. And also going back to this idea of navigation, there in the subsurface, drilling is a very complicated environment in that there's no reference sometimes, or there is typically no reference. So drilling kind of creates its own navigation or coordinate system. And so you can actually find a loss in directional drilling accuracy when you have an increase in solar radiation. And one interesting event was back in March 1989 when a very powerful solar flare hit Earth and actually created a 9-hour blackout in Quebec, Canada. And so you can see the solar flare here mapped on the sun, and you can actually see the event here. And we're talking, so usually it's pretty quiet around 0 nanoteslas if we're thinking about a residual field, but certainly becomes extremely strong. And this can saturate the transformers and cause complete breakdown in the navigation and electrical grid. I'm going to take a slight detour now away from magnetics, but still staying in the realm of electromagnetics. And so going back to our ground penetrating radar, we have our geophysicist here, our transmitter and our receiver. However, we're going to take that transmitter and receiver and move it off the ground and put it onto our drone. Now, this system is very effective. When I say this system, GPR, is very effective for archaeology, infrastructure being assessing the quality of, let's say, concrete. Is it starting to degrade? We can look for utilities, buried pipelines, quality of rebar, and then also looking at geohazards such as avalanches, which I'll talk about, environmental implications, ice thickness. So it's it's very broad in terms of its application. So this is a system that SINTEF has, and we have a high frequency system at 1 gigahertz, and then we have a lower frequency system going from 75 to 400 megahertz. And so we have literally put it onto a commercial off-the-shelf drone, the DJI M300. The only thing that's been modified is, for example, with this particular GPR system, it is unshielded, which means that the radar signal can go in all directions. So it would actually be impacted by carbon fiber legs. So kind of that discussion I mentioned earlier about this idea of platform noise induced eddy currents. So we actually have to swap out our carbon fiber for some plastic legs. And the examples that I'll show are actually part of SINTEF's GeoDrone project, as well as Geosphere, which were geohazard survey from the air, which was a partnership with the Norwegian Geotechnical Institute and the Norwegian Road Administration. So I'm just putting up a video of a recent drone GPR survey that was collected in the Swiss Alps as a collaboration between SINTEF and the University of Grenoble Alps. And so you can actually see the drone in flight here. We fly very low to the ground, typically 1-2 meters, because we need to be as close as possible to reduce the amount of attenuation in the air. So what happens is that that signal is going to be lost depending on how many layers it goes through and depending on the medium. So what is the material? For example, it will be stopped dead in its tracks in salt water. So also you can see here that the antenna is very wide. So that is showing us that it is a low frequency system. And in terms of this case, this is really important because we're looking at the thickness of this ice sheet, so of this particular glacier within the Swiss Alps. Just mute that. Oh, it's mute that, there we go. So moving on to a particular test site that we have here in Norway. And so this is the Norwegian Geotechnical Institute, Bombu. And so we've been working there for the last 4 years with the main objective to understand avalanches and the different structure of the snow and ice. So we've been collecting drone GPR since 2021. And we can see an example here of some of the profiles collected from the GPR. We have air, snow, and rock. And this is a very high resolution data that was collected recently. And what's normally done, or I should say what was normally done, is all of these interfaces are picked manually, which is extremely tedious and extremely time consuming. So there's a push to making this more automated. And so here is an example based on the master's thesis of Martin Chotel from École Polytechnique that worked with us in terms of setting up this automatic picking of an interface. And why this is important is that the more interfaces and picks we can get, we can create better training data sets for later on if we apply machine learning. And so from a machine learning perspective, I'm I'm showing one here that is actually originally used for seismic data to be able to look at the first break. So by picking the first break on a number of these profiles, we're training the data set to find that first break in the data for subsequent. Now, the thing is, looking at transferring this idea of machine learning to pick the interfaces in GPR data, which is similar, but some of the properties are definitely different. And it is still a very complex, complex system in that when we're working with snow and ice, we don't always know, it's not always clear some of these interfaces. So it's definitely very difficult. And kind of like what we saw with the magnetic data, we can collect all of these profiles and start to create a lateral map of the area. And so here we're comparing our ground penetrating radar to, once again, this LiDAR point cloud that's collected. Now, the LiDAR data is collected, for example, in this case, we're getting the snow height. So we're getting that surface of the snow. However, in order to determine the actual snow depth, we need to have a baseline. And so either there has to be a pre-existing LiDAR data that was collected during summer when there was no snow, or we have to have a DEM, a digital elevation model, to compare to. If that baseline doesn't exist, then we have nothing to be able to determine that subsurface thickness or height. This is where, once again, geophysics is very beneficial. It gives us that snapshot below the ground that we normally wouldn't have. And GPR will give us, through the application of our interface picking or processing, interface picking, and then potentially machine learning to determine the properties and height, that we can actually get a real idea in real time what the snow height is. And this year, when we collected data at Fambu, working with the Norwegian Road Administration, actually collected one of the first beyond visual line of sight flights with GPR. And so this was actually collected over the avalanche zone. And so we can actually start to understand each part from the top, middle, and bottom section of an avalanche zone, and to see what are all of these very intricate layer tracking. So we might have different crystal structure within the snow and the more ice or more moisture. And so we can actually really start to see all of these individual components within the snow layer. And it's really important to be able to help the snow scientists in terms of their prediction. And this area is incredibly important because quite literally off to the side of this avalanche zone, there's a road and a tunnel. And so need to have very careful consideration as the probability of an avalanche runout. And so this is a security and safety concern. And this is very true for a lot of areas within Norway, for example, and parts of Canada that have very steep topographic relief and might be more susceptible to avalanches, landslides, rock slides. We need to have that predictive method or forecasting to make very critical decisions in terms of the transit network. And going on, kind of following up, there was Ben Evans' presentation a couple weeks ago, which was really nice to see this sea ice monitoring network. And so we have also been doing ice height and snow height. And so with this, we employed two different antenna frequency ranges at Ufona, which is one of the oldest onshore ice sheets within Norway. And with the 400 megahertz antenna, we can see that we're getting down into that ice, but we're not seeing the bottom of it. We only see the base of the snow. By using a lower frequency antenna, we can actually start to see the base of the ice. And so this is really important to not only look at the snow coverage for avalanche or other implications, but even the ice depth And so this is a really important conversation around climate change and with melting glaciers. And drone GPR is fantastic at being able to provide an insight into that, and we can map it. And again, kind of referring a little bit back to Ben Evans' presentation, there was a discussion of this node system. And so I wanted to address that here at SINTEF, for example, we have a project called SPARSE, and it is a very large collaboration with all of these individual companies, universities, looking at monitoring of post-carbon CO2 injection. And so we basically want to look for a long-term, low-cost geophysical monitoring, which would be based on sparse node system. And this is going to be in very harsh climates. So we're looking at, for example, in this case, offshore at the sea bottom, we want to have a node. And because this is a very harsh environment in terms of temperature, turbidity, we need to start looking at similar equipment that the defense market would actually need to use and be able to have that repeatability and that sensitivity. And so we have this discussion at the end of the day to make sure that we have a reliable network that can be implemented for onwards of 30 years. And a lot of the Arctic is also, a lot of the monitoring uses satellite, as I briefly mentioned earlier. And so the benefit is that we can cover a lot of data or a lot of area more effectively. And it's non-invasive. However, we need to be able to ground truth this. And so we need to create a bottom-up approach. And so I highlight work done by previous colleagues from the Research Council, Pablo Arroyo and Ray Sofer, and then Margaret Kalaska from McGill University, who did a multi-year campaign over Mer Bleu, which was Mer Bleu peatland, which is an Arctic analog just outside of Ottawa, Canada. And so over the span of years, they implemented very precise and repeatable measurements for laboratory, field, drone, airborne, and then satellite. And so for them to be able to create that tie between each stage of the data collection, as well as understanding what information is retained and what information is lost as we continue up, we scale up through the different methodologies. And within the physical sciences market and geosciences, there's back in the last 10 years, there was a lot of emphasis for the Canadian Arctic to understand how to do geological mapping, which you can see here in the middle, without actually having to be on site. Geological unit mapping, bedrock mapping was typically done by foot with a geologist to map specific contacts. So you had to have an outcrop. You had to be able to stand on this geological unit. So the hope was by having a number of different layers as an input into your machine learning architecture, in this case, random forest, to be able to produce a probability map of the individual geological units. Taking this in another direction, we can use this for mineral exploration. And again, this is in the Canadian Arctic and looking at the magnetic data, but what are some of the structural components? What are some of the smaller targets? And can we find mineral resources? And so this is an example from the Northwest Territories in Canada. The Geological Survey of Norway has also been doing a lot of really interesting work in looking at compositional data of geochemical data, as well as machine learning to look at the potential for mineralized and non-mineralized zones. So I've talked about magnetics and I briefly mentioned radiometrics. But even within all of these, there's more information that we can get from each of these data sets. So for topography, we can look at slope and aspect. We can look at vertical derivatives, tilt derivatives within magnetics, and so forth. So all of these can add individual layers that can help train our model for machine learning. and be able to predict mineralized or not mineralized. And it can also help guide us when we start doing subsurface inversion to really start to understand what does our target, whether it's a geological unit, a UXO, what does it look like based on the information that we have put together from the machine learning algorithm. So to kind of finish this off, I want to address a couple of the key challenges that we encounter by doing physical sciences in the Arctic. So from an operational standpoint, obviously it's cold. I think we saw that in the previous presentations. It's the thing is, it has an impact on our platform and our instruments. Our platform might not be able to operate as long because of the battery limitation. Our sensors might not even be able to warm up and actually be able to start collecting the data. And we've encountered this working at FOMBU in terms of our GPR. And I know of other groups, for example, working in Iceland with magnetometers, they could not get the sensors to work because it was too cold. And you literally have to warm them up sometimes with a blanket to get it operational. And so we have snow, we have high winds, which can make it incredibly dangerous, steep, rugged topography. And in the case of some of these drone flights, we're flying extremely low at 1 meter and not just across flat surface, we're going up the steep surface. So when we look at our platforms, we look at our sensors, they're, you know, lab does not equate to the real world. So what we see in the pamphlet is not necessarily what actually happens in real life. And in Norway, we have high vegetative cover. So when we're thinking about the satellite data that we might want to use, we can't see past the canopy if we want to look and understand the rock underneath, or any target for that matter underneath the tree line. And so we have to take this into consideration, and it can actually have an impact in terms of when we're flying and obstacles. The magnetic field is certainly much more variable as we move towards the polar region. We have a very magnetic declination can absolutely have an impact on our navigation capability, and compasses can be completely moot in some spots. And I think something that a lot of groups are encountering are restrictions on hardware. And for example, in the US, I think that others can speak better to this than I can, but the inability to be able to use a DJI drone that we use here in Europe. And so it's fine for the defense and security market that can design their own platform, their own sensor, because they have access to the resources and finances to do it, but not from the research side, the academics, the scientists. And so there's collaboration between the scientists and, let's say, the defense and security market. But what happens when we have that overlap and the working together is that the data becomes protected and cannot be publicly released. And that, as a scientist, is extremely limiting. And so what happens is, by putting limitations on the hardware, the sensors, it can indirectly impact the quality of the science that is being published and actually slow it down. So just some final consideration. I think an important aspect is that there always has to be an open dialogue for any work that's being done in the Arctic. And so the first being community feedback. Before doing any of our operations, we always try to make sure that those in the area know what we're doing and why. So for example, here, when we were flying our drone magnetics in southern Norway, you can see here Suzanne McEnroe from NTNU and Unide and Odeshard from Helmholtz Institute, showing the drone system to the school. And we made sure to publish all of our work within the newspapers so that when they saw us flying, they knew what we were doing. And in terms of, especially within Northern Canada and Northern Scandinavia, being respectful and having an open dialogue with Inuit, First Nations, and indigenous populations. We need to have an awareness of what it is that we're doing. We're typically doing non-invasive methodology. However, it can still have an impact in terms of those that actually live and rely on the land. And then finally, this idea of we want to be able to transfer the knowledge that we're learning and gaining from the collection, and be able to disseminate it to all relevant parties, and so that we can extend the science and really continue to have the dialogue beyond the current geophysical survey that we've been doing. So to finish up, I think having a physical scientist as part of a team within defense, security, machine learning is incredibly important, because they understand the environment as a whole and are able to help provide context in terms of what may be limiting in terms of finding that needle in the haystack. And with the impact of climate change, physical science really plays an important role in terms of unlocking what is required to support global demand of resources in a sustainable and respectful way to not only the environment, but also vulnerable communities. And so with the changing landscape, we need to look at more specialized hardware, analytical techniques to forecast changes, as well as to be able to estimate the geometry and the depth of particular targets. They're becoming far more complex, and so we need to be able to have a good understanding of that. And I just put this down here, which is the looking at decision making and modeling for nature-based solutions. So always making sure to have the environment as an actual part of the scientific method or the research opportunity that is being undertaken. So I will finish up there, but I really appreciate the time to talk about this today. And certainly we at SINTEF are always very happy to discuss collaborations, consortiums, especially within Europe, Canada, the US, because we recognize that there's a lot of really diverse work being done out there, and we'd love to look at collaborations. Thank you.
Madeline, thank you so much. That was such a fantastic presentation. It is something that is so out of my wheelhouse, but you were able to explain a very kind of technical subject and a technical kind of set of processes and technologies in a really clear way, and really speak to the utility of it, but then also your maps are great. I loved the space weather map. That was so cool. So like A+ visuals. I think I have a few questions, and this is coming from my background as a historian and as someone who does Arctic security policy. One of the things I found really compelling is your discussion about the processes of community engagement. You know, making sure that you go into these communities and you not only communicate with them, but also I thought publishing the data in the newspaper as a means of really contextualizing why something is flying overhead is like really, really important. And so I was wondering, the first question that I have, what are some ways that you think this information or the scientific kind of processes and data that's being collected could help those communities? Also, what has been the reaction that you've gotten from community members about this?
Yeah, absolutely. And I think that's a really good consideration and question. So the first thing is that, you know, coming from drones, for example, I've been working with drones for about 11 years now, and I have seen a change in the hesitancy. So when we would first fly a drone, people were extremely nervous and they didn't like it. There were lots of photographs, and we had to tread incredibly carefully. It's definitely relaxed a lot more. So having that interface and being very honest at the beginning with what we're doing actually helped ease the anxiety and stress of the community beforehand. And I think that's really important, because that's their home. This is their space. This is their privacy. And we're coming into it, and we might be taking information that they're not comfortable with. And so giving them an opportunity to raise concerns ahead of time also creates a really respectful sense of communication. And as scientists, we need to understand that, yes, we would love to be able to collect all the data we can wherever we want, but sometimes we just can't. And so The other thing too, for example, is that there's again, with the Society of Exploration Geophysicists, there's Geoscientists Without Borders. And so they've been around now for, I think, since about 2010. And so they have done extremely good humanitarian work around the world using geophysics. And a key part of that is that it has to be engagement with the local community because they understand the environment, the land, and what's actually going to work far better than any of us coming in there. We can have our idea, but they actually know, you know what, this isn't going to work because I actually know that the water runs that direction. And you want to do your survey over there? No. So it gives us an opportunity to improve our methodology and to have a data transfer. And with Geoscience Without Borders, it's been really nice to see some of these projects that were started. For example, some were like a European university going into Africa, doing a geophysical survey, teaching different skill sets, and then it actually created a new Geoscientists Without Borders project in another area within the country. And so just to really see that snowball and provide training to other community members.
That's fantastic. And I first off, I am excited to kind of look up geoscience, what the organization that you just said. We do have a question that's a little bit more
Yeah.
technical, so I will get to that. But just one kind of comment, and maybe we can return to that. But what I wanted to note is, especially in terms of technology, especially weather data, anything that's really gathering data about Arctic space,
Mm-hmm.
there's a lot of assumptions around it, especially geopolitically. There's a lot of skepticism of whether meteorological stations in the Second World War, or even now, satellites, drones, a lot of these machines that are used for scientific purposes can also be
Mm-hmm.
skewed to be understood
Yeah.
as part of, defensive measures, part of,
Yes.
bringing conflict into the space. And so I think the kind of discussion about the interpretations of these machines and what they're doing is really important, especially as we see the potential for the geopolitical conflict to be heating
Mm-hmm.
up in that. And I think kind of questioning, and so that's why it's really interesting you're talking about socializing or introducing this kind of drones to the local communities. However, we're going to transition too, because I want to talk
Yeah.
about this. But one of the questions from the chat is, could you please elaborate on the machine learning implementation? Is the goal to, for example, predict or extrapolate from sparse measurements?
Yes, actually, that's a really good comment. Sparse measurements, and so that's where it's highly applicable for Arctic regions. So here in Norway, it's a small Arctic country, so it's a lot. In some ways, it's easier to access these remote locations to collect data, so long as you also have the issues of the mountains. But in Canada, the Arctic region is so vast. So to be able to physically map either mineral potential or even geological contexts or anything for that matter, different types of vegetation is very time consuming. And so there has been data collected that is verified from ground truthing. We have substantial airborne or satellite data that is publicly available. It's fantastic the amount of satellite data that's publicly available. So by creating these training data sets or these parameters, these constraints with the previously collected sparse measurements, to help direct the machine learning architecture is really important, and certainly helps expedite it. However, with all of it, having someone with experience in the area, taking a look at the final result is incredibly important still.
Fantastic. Okay, we are going to wrap it up. And I just want to sincerely thank you so much for what a great and educational, but also very accessible presentation. And also thanks to both James for helping us run this and Phil for his just ceaseless leadership in this whole endeavor. So I just want to give a quick plug that next week we have Dr. Raman Shafer, he will be talking about kind of indigenous rights and kind of really looking at kind of the intersections between indigenous indigenous rights from an international law perspective, and the environment and Arctic security. So I'm very excited to bring that perspective in. He is a professor up at the University of Akureyri in Iceland, where he teaches international law in an Arctic context. And he's also the director of the Arctic Institute, and he's also a really awesome person. So next week, we will send out all of the information of that on the email, and I'm just super excited for all of you to be here. I hope you all have a nice rest of your day. Thank you.